Got it. Okay, so now that we're talking about covalent bonding this week instead of ionic bonding, we're going to find that there's a lot of chemical formulas where it's like you can't just use the charge to determine like what the ratio of things should be and how they're connected to one another. Each of the atoms will have a huge impact on its overall chemical reactivity. And a lot of chemical formulas can have very different ways that the atoms are connected for any given chemical formula. We call these isomers, like different ways of arranging the atoms. So I'd like to walk through just like how to interpret a chemical formula into a possible Lewis dot structure. And for a lot of these, there's lots of possible answers, not just one correct answer. So that's also kind of gives it this open-endedness that's a little challenging in the beginning. So just stop me if you have any questions along the way too. So this one has a nitrogen, an oxygen, and 3 hydrogens. What I typically do when I'm working with these is I first, I draw out the Lewis symbols for them. So these are just looking at the number of valence electrons and draw it around to kind of think of these as puzzle pieces. And this isn't a style that everybody does. This just works well for my brain. So I can show you another way too. And I've got 3 of these hydrogens. So what I know about each of these elements is that nitrogen has 5 valence electrons, oxygen has 6 valence electrons, and hydrogen has 1 valence electron. And I get this information from their location on the periodic table. So a lot of people who teach this also like to suggest that you count up the total number of valence electrons for the molecule. If you were going to do that, you would say, all right, well, I've got 5 for my nitrogen plus 6 for my oxygen. So now I'm at 11 plus 1 for each of my hydrogens. And I've got 3 of those. So that would have 14 total valence electrons. The idea is that you count up the valence electrons you have, and then at the end, after you make your structure, you can count up the electrons you used and make sure you still have 14, that you didn't forget any and you didn't add any. Also, there's a style of solving these where you choose where you want the atoms relative to one another, and then you just kind of like add the electrons in as bonds, and then any extras become lone pairs until you get to that number 14. That's a totally legitimate way to do it. I find that it leaves a lot of guessing at the beginning for students that haven't developed chemical intuition about which atoms tend to form which bonds with one another. The method that I like, because it takes some of that guesswork out, or that it doesn't rely on intuition, is that we use the number of valence electrons to predict the number of bonds that it's likely that atom would form. So in general, for these, the number, let's do this in a different color. The number of bonds an atom is likely to form is going to be equal to 8 minus its valence electrons. And this is really similar to what we were just doing with ionic compounds, right? Like you have 5 valence electrons. That means it'll probably need 3 more to get that magic octet number. And so this is really based on that octet rule. And this time, instead of it being electrons that it needs to gain to be an ion, it'll be bonds that it needs to form to reach that octet by sharing electrons. So with that in mind, for our nitrogen, it's likely that we're going to have 8 minus 5, that's 3. So we'll have 3 bonds. Oxygen's 8 minus 6, so that's equal to 2. So we'll have 2 bonds. And hydrogen's different. Hydrogen doesn't follow the octet rule. It follows the duet rule. So it's really 2 minus 1 equals 1. So it'll form 1 bond. So that's kind of the weirdness of hydrogen. It's never going to have more than 2 electrons around it. It just can't. It doesn't have the ability to support that. So then with this information, I start crafting my like 2D picture of what this molecule might look like. And there's a couple ideas about how to start. Some common advice is to put the, the least electronegative there we go, atom in the center, which is usually the case. I would like to say, though, that there are some exceptions to that. Like hydrogen is never in the center. So just following that rule kind of in a blanket way won't work. So I actually have a different one that I tend to follow. Instead, I say which atom needs the most bonds to form an octet. So I put the most bonds in the center. And here, nitrogen needs the most. So I'm going to start with nitrogen in the center. And what I do is I put in the valence electrons for the electron dot symbol. Some strategies will say just put the atom and then arrange the things around the atom, envisioning that you're using the four sides of the atom and then just add in the electrons. And I don't do that because I find that then I get lots of atoms that have actually too many electrons around them, or it's hard to see where to form bonds. So what I do is I use these to kind of guide me. So I know this nitrogen needs to have 3 bonds. And really, if I look at this, I have 3 unpaired electrons. So that's where I'm going to form the bonds to my nitrogen. Anything that is lone pair already, I'm going to leave that alone. So I'm going to leave all lone pairs alone, which means I won't form a bond to it. So, okay, so I've got my nitrogen. Next, I put in the next most bonds needed into my picture. So in this case, that's going to be oxygen. It's going to need 2 bonds. So I'll place that next. And I can form a bond to this nitrogen anywhere I want, but I'm going to link up to one of these unpaired electrons. So I'll go ahead and put my oxygen here. And again, I'm going to use these electron dot symbols to kind of guide where I'm forming my single or double bonds. And so I have an unpaired, I've got on oxygen 2 lone pairs, and I have 2 unpaired electrons right here. So I'm going to link up my unpaired electrons, and they're going to form a single bond. And I literally do this, like connect the dots on my draft and then just redraw it so it looks better. And this helps me keep track of my electrons, so I'm not adding or subtracting any. It also helps guide where I place the atoms, and it gives me a rule set to minimize the amount of guesswork that I'm actually doing on this. So I like a nice algorithm more than anyone else probably. So again, I'm not going to mess with the lone pairs. Those I'm going to leave alone. I'm not going to separate them unless I have to. And I'm going to form a bond between 2 unpaired electrons. Okay, now I've placed my nitrogen and my oxygen. The next thing I need to do is place my 3 hydrogens. So at this point, I'm going to go ahead and count and say, oh, all right, well, how many unpaired electrons do I have left? So at this point, after placing, I have 3 unpaired electrons left. I have 3 hydrogens. So I'll bond 1 to each hydrogen. So that means I'm going to place my hydrogen here. Oh, a hydrogen here and here and here. And I'm going to go ahead and I'm going to connect those dots again, right? Excellent. So now I have basically a draft and I can look at this, and my question to double check myself is, so it's like 1, 2, 3, double check. So to do that, I'm going to make sure that my nitrogen and oxygen have 8 electrons around it, and that my hydrogen has 2 electrons around it. I'm going to do this by adding up lone pair electrons and bonded electrons, or shared electrons. Put it like that. So for example, then with my nitrogen, I have 2 electrons in the lone pair, and I have 3 bonds, each with 2 electrons in it. So that's going to be equal to 2 plus 6, which equals 8. Woohoo! I've got 8. So that nitrogen looks fine. For this oxygen, similarly, I have 4 electrons in lone pairs. I have 2 bonds. Each has 2 electrons in it. So that's 4 plus 4. That's 8. Great. Double check. So my double check here is in pink. Note that when I did that, this bond between the oxygen and the nitrogen, I counted those electrons both when I was assessing if the nitrogen had 8 around it. And then I counted them again when I was assessing if the oxygen had 8 around it. I'm going to, instead of thinking of the whole molecule, laser focus in on one atom and look at everything that's around it. And then when I look at the one next to it, I'll look at everything around it, even the ones that were shared with the one I previously counted. Both of my hydrogens both have 1 bond then. So they have 2 electrons in a bond. So that's just 2. That's great. So my hydrogen checks out at 2. I can also now go and count all of the valence, all the electrons in my Lewis structure if I want. So I can compare total. So I had 4 valence counted before. So I need, or sorry, 14. So I need 14 valence or 14 electrons in my structure. So I have, let's see, I have 1, 2, 3. I have 3 lone pairs. That's going to equal 6 electrons. And I have 1, 2, 3, 4. I have 4 bonds in the molecule. So that's going to be, each of those bonds has 2 electrons in it. So that's going to be 8 electrons. So 6 plus 8, I'm at 14. So that double checks too. So now I have a Lewis dot structure. If I wanted to redraw it to be pretty, I could do that too. It's going to be a nitrogen bonded to an oxygen, bonded to a hydrogen, and the nitrogen's bonded to 3 hydrogens as well, or 2 hydrogens. And I have lone pairs on my oxygen and nitrogens. And so this would be a Lewis dot structure for it. At this point, it's in 2 dimensions, and I could start thinking about its overall molecular shape too, and looking at polar and nonpolar bonds. So thinking about molecular shape, with this, what I would do is I would recognize like what are the different atoms that are bonded to a central atom, and a central atom is just going to be anything that's bonded to more than one thing. So my only central atoms that I have here are my nitrogen and my oxygen. These hydrogens are terminal, like they're just bonded to one thing, so they don't actually have like a shape associated with them. But this nitrogen right here is bonded to 3 atoms, and it has 1 lone pair. So these 4 things will repel each other. And they're going to repel each other. So they're, because they all are balls of essentially negative charge, right? The electrons are all negative, and so they're going to repel one another, like charges repel. And so they're going to arrange themselves around that nitrogen so they're as far apart from each other as possible. And four things can get 109.5 degrees away from one another. And now the lone pair is going to take up more space. So it's going to kind of like push everything else in a little bit closer. So it might be more like 107. It might be more like 107.5. The only way to really actually know is to like study this molecule by making a crystal of it and seeing exactly what those bond angles are. And a lot of textbooks just give you, they're like, anything around a nitrogen is 107. I was like, well, not really, but it's a nice abbreviation. I don't think it's worth memorizing. So these are all going to be around, but only 3 of these are going to be actual atoms. And so our geometry is going to be based on the number of atoms that are bonded rather than the number of things that are repelling. However, that overall shape and the bond angle will depend on all the things that are repelling. So 3 things bonded and 1 lone pair will always be trigonal pyramidal. All right, let's look at oxygen and then we can draw this in 3D. So oxygen, we'll do it like this, is going to have, in this case, or in many, it's going to have 2 atoms bonded. And it's going to have 2 lone pairs. So again, this is 4 things repelling. So they're going to be about 109.5 degrees apart. Again, a lot of books are going to say 105 for most oxygens. There's 2 lone pairs and they take up more space. So they're going to push things even closer together. So it might be about 105 to 109. Similarly, like the nitrogen was about 107 to 109. And for me, at least, like you don't have to have that perfect. I don't think it's going to make a big difference. The geometry that's associated with 2 bonded atoms and 2 lone pairs, so like those bonded atoms dictate it, that's going to be called bent. So now I can draw this in 3D. So our nitrogen is going to have those 4 things around it. It's going to have that lone pair, right? And it's going to have everything 109.5 apart. And so the way to draw this, so I'm just going to choose any old atom, right? So here's how to draw 4 things 109 apart-ish. It looks like a jack, if you've ever played jacks, like the kid game. But the idea is that each of these are about 109. And you have 2 that are kind of in a plane and then 1 coming out at you and 1 going back. And this wedge is, this dashed line is going back into the page. And this wedge is coming out of the page. And this is our shorthand for drawing in 3 dimensions for chemistry. So with this nitrogen, I'll have 1 going back, 1 coming forward, and 1 going off to the side. You can imagine this lone pair here is coming straight up, right? But we don't need to draw the bond for the lone pair because it's not actually a bond. So I'll have my hydrogen here, a hydrogen here, and then my oxygen will be bonded to this nitrogen. Now the oxygen also has 4 things around it. So it's using this same kind of 3D shorthand that we're going to use. And especially for bent, I like to take advantage of the fact that we have 2 of these bonds that are in the same plane. So I'm going to do that for my oxygen and say, all right, well, the other one's right here. That's going to be the hydrogen. And then I have essentially like this wedge and dash to the lone pairs coming out. And if it helps to put the wedge and dash to the lone pairs, please do. The way we tend to do it in chemistry that you'll see in books and online resources is we'll just draw the lone pairs like that. And then we can label the shape. So like this oxygen is bent, and this bond angle is about 107 to 109. This nitrogen right here is trigonal pyramidal. And each of these bonds around the nitrogen is at about 107 to 109. Sorry, I meant to say 105 for that oxygen. And that's how you would interpret it into 3D. Okay, I am going to stop there, see if there's any questions.